Hello, my name is Jeppe Kristensen, and I will be talking about our paper Personalized Game Difficulty Prediction using Factorization Machines. This is a collaboration between both the IT University of Copenhagen and Aalto University, as well as Tactile Games. The goal of this paper is to do individual difficulty prediction. So imagine we have a group of users or players, and they have to complete certain tasks. But not all the users have encountered all the tasks yet. So what we want to do is to estimate how will they specifically find this task instead of just using the historical average of the other users. For this purpose, we use factorization machines, and we validate our approach using a case study from a mobile puzzle game. Factorization machines are a matrix factorization method where the interaction between users and items is enabled through a latent feature description. So specifically for factorization machines, for example, the target Y here can be described by some global bias. The bias for each of the features that you would typically have. So this could both be whether it's for a single user, for a single item, or maybe some more descriptive features. And then lastly, the latent interaction term here, where we have some interaction features V and the second order interactions between x1 and x2. In order to validate our approach, we use data from the commercial game Lily's Garden by Tactile Games. It's a mobile puzzle game where you have to complete a number of goals within a certain number of moves. The game is not deterministic, so the colors that drop down and so on depend on the random seed, and thus you cannot always be sure that one tactic works in all iterations. In this paper, we considered the first 500 levels of the game, and in order to operationalize difficulty, we use the attempts that people spend to complete the level. On the right, you can see how the average number of attempts changes over the course of the first 500 levels, where easier levels require on average close to 1 attempt per complete, and harder levels require up to 7 attempts per complete. One thing to note is that the distribution of attempts is very long tail, so you can have in the harder levels players that spend upwards to 30 attempts per complete. We use data that spans around 6 months in this period here. In order to create a training set for our model, we first use all the data up until a given point, which is the observed levels for all the players, and then we take the data from the remaining 99% and all the levels that we have available. We test our methods on the remaining 1% of the users after level 150. What we see is that in order to beat our baseline that consists of the average of the other players in the training set, we need around 20 to 30 observations in order to beat that. We also see that random forest, which is the purple here, fares better with fewer observations, but as we include more and more data, it performs worse than our factorization machine model. Lastly, we can also see that the effect of including additional data, such as some player features or level attributes, helps the prediction of the factorization machine. In addition to investigating how many observations of the players we need, we also provide an interpretation of the model parameters. In this case, we consider the two-factor model, which provides us with 3 parameters to explain: the variable biases, Wi, and the 2 latent factors, V1 and V2. For the variable bias Wi, we first note that for the levels, the average number of attempts is strongly correlated with the level bias. This suggests that the level bias here captures the average difficulty of the level. For players, we note that the biases are centered around 0 and therefore capture some kind of variation or small variation between the players. For the first latent factor, V1, we note that for most of the levels, the latent factor is above 0. This suggests that it captures some kind of intrinsic variability of the level, which is supported by the graph on the right. It shows that the variation in attempts increases compared to the mean of the attempts as the latent factor increases. Furthermore, tutorial levels are clustered to the left at low values of the latent factor. Common to many tutorials in the game is that they are deterministic and use specific random seeds to ensure similar experiences. For the players, the latent factor instead captures some kind of skill or their ability to deal with stochastic elements. The larger the absolute value of the latent factor is, the more susceptible they are to random elements of the game. The sign then indicates whether it increases or decreases the number of expected attempts they will use. For the second latent factor, V2, the results are less clear. For both the levels and the players, the values are all centered around 0, and on the graph to the right, we can see a clear dependence on both the level number and the average number of attempts on the level. We therefore interpret the parameter as some kind of time-dependent descriptor, which for the players captures their ability to learn over time relative to the rest of the player base on these levels. Overall, we find that factorization machines provide an accurate and scalable method for personalized predictions of the perceived difficulty. The method performs better than the baselines using either historical averages or random forest, especially once more observations are included. The method is also game, task, and domain agnostic. In any problem where user-item interactions can be described using a multiplicative or divisive way, factorization machines can be used to capture these latent interactions for any kind of regression target, such as time taken or similar. Lastly, it's also possible to include additional data, which could be tags, labels, time, user features, task attributes, and so on. However, one thing that has not been considered is how to deal with the cold start problem, which is when there are no observations of either the player or the levels. While additional data can help this issue, future work can look into how to best to deal with this problem. Thank you for your attention, and unfortunately I couldn't be there in person, but I should be in the chat now to take questions.